So I'll go mainly on three topics. Well, I split basically the talk on three topics. I will first introduce a bit of background. What are side channels? What are these observational models that we use to verify software, or at least to verify absence of side channels in software? And one of these famous attacks that break security of many of existing models is called Spectre. Then I will go to a mechanism to validate existing model using testing, using basically model-based testing. And then I will then optimize a mechanism to optimize this testing approach using model refinement. So this is basically a sort of application of model-driven testing, symbolic execution, non-interference, refinement, and SMT to security. So basically, it's a mix of formal method and security. So let's start with a bit of background, right? So when we define confidentiality of programs, we often rely on the concept of non-interference. That means to define that the program satisfied does not leak some data, we classify the input of a program as some let's say, classified data and public data. And then we ask basically that the program, they ask the program to be non-interference. That means that for every two initial states, A and B, that are indistinguishable for the attacker, that means basically they have the same public input. When we run the program P with the input A and we run the program P with the input B, then this program produces basically an output that is indistinguishable for the attacker. It basically produces the same output, okay? And they, of course, can produce different secret input, but the public output should be the same. And when we deal with side channel is that, well, side channel are basically some microarchitectural feature like a cache hierarchy, hyperthreading, pipelines, multi-core behavior, speculative behavior, and so on and so forth, that may be affected by this classified information and can be measured by the attacker. So the attacker is able to distinguish different execution of a program from two different states that only differ for some classified information by looking at this microarchitectural feature of the processor and use then this measure to extract, for example, cryptographic key, password, and so on and so forth. And I show here one of the simplest example of a side channel. And this is an access-driven attack based on cache. So suppose that in our system, we have a large memory, for example, I don't know, 8 gigabyte of memory, and a small cache here on the left side. So cache can be shared between a victim and the attacker. And the cache is usually organized in small blocks. In this case, each cache line. So in this case, a cache of 4 kilobytes will consist basically of 64 blocks, 64 lines. The memory is transparently mapped by the processor to the cache. That means the first 64 bytes in the memory will be mapped to the first cache line. The second 64 bytes will be mapped to the second cache line, and so on and so forth, right? Now, suppose that we split this memory between some memory that is accessible by the victim and the part of the memory that is accessible by the attacker. So now the attacker and the victim run on the same processor. The attacker may prime the cache. That means it reads some region of memory that belongs to its own address space. And by reading this region of memory, it primed the cache. It filled the cache with its own data. So in the first cache line here, we will get the content of this memory region that belongs to the attacker. Then the attacker gets scheduled and the victim get activated. And the victim now reads into the memory in a location that depends on a secret. So suppose that this secret belongs to the first 4 kilobytes of memory, so a region of memory that is not accessible by the attacker. But by performing this memory read, the victim may access a memory region that is also mapped to the first cache line, where the attacker has first stored its data. This will force the CPU to evict the existing data of the attacker and to fill this data with the data of the victim. When we execute the attacker again, the attacker can now probe the cache by checking how long it takes to read the address for kilobyte. If the victim has not accessed the first cache line, this data is still in the cache, so this memory access will be fast. Otherwise, if the victim has accessed the first cache line, then this data has been evicted from the cache, and then this memory access will be slow because the processor has to fetch this data from the main memory and load this into the cache. So in this case, the attacker is able basically to extract some information about the secret by not reading the memory, but just measuring how long it takes basically to perform this probing part. So now there are many types of side channel. There is power consumption, electromagnetic radiation, sound, temperature. We mainly focus on this timing attack, often that depends on cache. And the problem is that it's unfeasible to have a precise deterministic models of these channels. The reason is mainly because on modern computer architecture are just too complicated to have a precise deterministic model of how a program affects the cache of a program over a cache, or how much milliwatt consume the execution of a program. And also, many of these side channels depends on many undocumented features. For example, for cache replacement policies usually is an industrial secret and is not documented when you buy a processor. You just know that there is a cache replacement policy, but you actually don't know what is replaced when you execute something in your program. So how we deal with this, right? So people have developed what we call observational models. They the basic intuition here is that we verify absence of side channels in a program by verifying that the program satisfy a sort of constant time programming policy, or we can call this a constant time observation policy. So we define abstract attacker observation that should over approximate the leakage that can happen when we execute an instruction. So they basically should over approximate the information flow, execute an instruction, which part of the state can be leaked and which part of the state can affect the side channel that can be measured by an attacker. So suppose, for example, we have this simple program here, and this program compared the content of two registers, X1 and X2, and in one case, it goes to the left branch. This left branch will perform two loads. And in the other case, goes to the other branch that read two locations in memory and perform an addition. Suppose that we run this program in a really simple microarchitecture where there are no cache, and the execution of this program only depends on the instruction that we actually going to execute at runtime. So even if we are not able maybe to precisely identify the execution time of the program, we may over approximate the side channel, that is the execution time, by saying that, well, the attacker can observe the result of this comparison, right? So we say that by executing this instruction that is a conditional jump, the attacker will be able to learn basically the equivalence between X1 and X2. This is an over approximation of the side channel because, of course, it may be the case that executing these two branches require exactly the same amount of time, but we want to be conservative, right? To say that the information that can flow into the channel is basically the equivalence between these two registers. Of course, in a different architecture, we may have a different observational model, right? So, for example, suppose now that we run the same program on a computer architecture, we assume that the attacker cannot measure the execution time of our program, but the attacker can measure the footprint that our program has over the data cache. In this case, a common observational model will require observe every single the location of every single memory access that is performed by this program. So in this case, this program will access the location X pointed by the register X2 and the location pointed by the register X4. And in this other case, the attacker will observe the location X2 and the value of the register X3 at this point, that is actually the original value of the register X3 plus 8. Okay, that's the intuition here, is that if the attacker can only observe the footprint and the cache, if we send the exact same sequence of memory access to the cache, the attacker should not be able to distinguish two executions. So for example, if we start from a state where the register x1 is 0, the register x2 is 0, we will go into this branch. Then if we read the location 1 to 3, and if we have the register x3 and the register x4 equal to 8, then this branch will read basically from 0, 8. And this state should be indistinguishable from the state where we have x1 equal to 100, x2 equal to 0, x3 equal to 0, and x4 equal to 42, because in this other case, the program will go in this other branch, will access still the location 0, like in this case, and then will increase x3 by 3, so x3 will become 8, and here we will also access 8, like in this case. So these two states, even if they're different, even they follow two different branches, should be indistinguishable for an attacker that can only observe the data cache. And we basically rely on this observational model to perform analysis of software and to verify if a software is side channel free. So now the question is, are these side channel models sound, right? Because we rely on this model to do the verification. So the hypothesis here that we want to validate is that if we start from two arbitrary states that are observational equivalent, that means they generate the same sequence of observation for the program P. It is true that if you run the program P on real hardware from these two states, there is no way for the attacker that has access to this specific side channel to take these two executions apart, to distinguish anything basically between these two execution. Because if this implication doesn't hold, then we have a problem, because we have program that can be wrongly considered secure. And the answer is that, well, many existing models are actually not sound. We have a famous example that is the Spectre attack that show that since many observational models do not take speculation into account and processor actually use speculation, we have considered for many years secure some programs that are actually not secure. And this, I just want to show you this example. So here we have a program that handle two arrays, the array A and the array B. And there's some cryptographic key that is outside these two arrays. So the array A contains basically index into the array B. So every element of A is an index basically between 0 and the size of B. The program receives an input here that is x1. It checks that x1 is within the bound of A. And if this is not the case, it just ends. Otherwise, it reads from the array A in position x1. It reads this into the register x2, and then use this index to index basically the array B and read the value into the register x3. So now this assumption that every element of A is a valid index inside B, and the initial condition here ensure that this program will never perform an out-of-bound memory read. This memory read will always be within the bound of A. This memory read will always be within the bound of B. And the observation of this program, if we assume observe basically the result of the condition and every single memory access, they only depend basically of the input x1 on the size of the array A, on the size of the array B, and the content of the two arrays. Okay, so if we run this program in a system and we assume that the attacker can observe, for example, the execution time of this program and the data cache, the effect of the data cache of this program, if we run this program from two states that have exactly the same array, but have a different cryptographic key stored outside these two arrays, the attacker should not be able to distinguish any difference. And that means the attacker should not be able to learn anything about the key stored outside these two arrays. Unfortunately, due to speculative execution, this is not the case. The processor may decide to execute these two instructions in speculation, even if x1 is actually bigger than the size of A. So if I provide as input to this program an input x1 that is actually equal to the distance between A and the cryptographic key, this instruction that can be executed in speculation, even if this condition doesn't hold, may read actually the cryptographic key and store this into the register X2. And then the subsequent memory load will access the memory addressing B depending on the cryptographic key. So this will leave a footprint in the cache that actually depends on the key. So even if these two states are observational equivalent, since we have not considered speculative behavior into account, the attacker will be able to distinguish these two states and learn some bit of the cryptographic key. Okay, and this is the problem. So our goal is basically to validate the models and devise a testing methodology to check if a model is sound. If it's true that two undistinguishable states, two observational equivalent states are indistinguishable on real hardware. And to do this test, we need basically three inputs. We need to generate programs to test the model. So we need to randomly generate program. And then we need to generate not just one state, one input state for this program, but we need to generate two input states that are observational equivalent. And once we generate these two input states, we then can test this state on the processor and validate it, check if the side channel are actually affected in the same way. So my focus here will be mainly on the test generation, that is how we generate these two indistinguishable states. And so basically the validation is done via testing. So this test generation consists of 5 stages, and it is a mix between symbolic execution, relational analysis, and use of SMT Solver. I will go through the 5 stages step by step. So the first stage, it allows us to be architecture independent. We basically transform the program that we receive. This is a random binary program that is used for testing, to an intermediate language. In this way, we don't need to couple our architecture to a specific instruction set architecture. So we can use, for example, a translation for RISC-V. We can have another translation for ARM, another translation for Cortex M0, and so on and so forth. So to support a different architecture in the pipeline, it's enough to define basically a new translation function that transforms the binary program into the intermediate language. So this is basically an abstract assembly language that is similar to the intermediate language of LLVM or Valgrind. We have an infinite number of register variables. We have assignment, jump, conditional jump, and so on and so forth. So if we take the program of before that I showed you before, this can be basically transformed to this intermediate representation where this condition here become a conditional jump that check the equality between these two arrays. And if this equality is not satisfied, it jumps to the address 12, otherwise it jumps to the address 4. And then in the address 4, this instruction that is an ARM instruction is translated to this operation that read from the memory from the address X2 and copy this into the variable X9 that actually represents the register X9 and then jump to the next instruction. And similarly here, we see in instruction 16 that is this addition. Well, this just set the variable x3 equal to the variable x3 plus 8 and then jump to the address 20. So from now, after this stage, basically everything else is platform independent and doesn't have to deal with a specific instruction set architecture anymore, but has only to deal with this intermediate language. Then the next step is to add observation. So for the same instruction set architecture, and we can have different observational model that represent basically different side channel available for the attacker. And each observational model is basically represented as a program transformation that inline observation into the intermediate language. So in the example of before, suppose that the attacker can observe in the observational model, can observe the result of conditional jump because it can measure, for example, the execution time of a program, then the model transformation will inline an observation here that say the attacker at this stage can observe the result of comparing the register X1 with the register X2. So it can learn basically the quality between these two registers. In the case that the attacker can observe every single memory access performed to the data memory, then in this case, the system will inline an observation every time that we read from the memory and inline basically the address that we are reading, right? So in this case, it had observation X2, here observation X4 because we are reading from X4, here observation X3 because we are reading from X3. Now, what you observe, it can be like different for actually the address that you read. For example, in many cache, in many processor, the processor read from the memory a full cache line. So if the cache line consists of 64 bytes, there is no difference for the processor for reading the first byte, the second byte, or the fifth byte of the cache line. There is no way for the attacker to distinguish between these two memory access. So we may want to inline some observations that are actually different from the address that is actually read from the memory. For example, we may want to mask this address with the mask that remove the offset from the cache line so that we can mask out this bit to say that the attacker cannot actually distinguish which part of the cache line is accessed by this operation. So for each basically observational model, we have a program transformation that inline this observation. Okay, once we have the annotated intermediate language program, we use symbolic execute all possible observation that can happen when we execute this program. This is basically an extension of standard symbolic execution, where additionally to the symbolic path and symbolic assignment, we also have a list of symbolic observations that keep track of what can be observed during the execution of the program. So again, I use exactly the same example of before. So when we start, right, we start before executing this instruction, we start from a symbolic state where the path condition is true because we always start from this instruction in this example program. And initially, each state variable is mapped to a symbol. For example, the variable x1, this is the first register, is mapped to the symbol s1. The variable xn will be mapped to symbol sn. And of course, initially, we have an empty observation list. Not up to this point, before executing the program, the attacker cannot observe anything. When we execute this comparison, assuming here we are assuming that the attacker can only observe the address that we are reading. So when we execute this comparison, well, we split the symbolic execution into possible states. In one state, we extend the path condition, but say that, well, we can go in this state only if the original value of the symbol S1 is equal to the original value of the symbol S2, and nothing else change in the state. Similarly, in the other branch, right, we say that we can go in this branch only if the symbol S1 is different than the symbol S2 and nothing changed to the other part of the state. Now, when we execute this load, two things happen in the state, right? So first of all, we need to change the value of the variable x9. Now is not anymore mapped to the symbol S9, but will be mapped to the symbolic expression memory load from the symbol S2, because now x9 is equal to reading the memory from the initial value of the symbol S2. But this also extends the observation list by saying at this point, I can observe the value of the register X2, and at this point, the register X2 is mapped to the initial symbol S2, so we extended this observation list with the symbol S2. When we increase the variable x3 by 8, assuming that there is no observation here, because we are assuming that the attacker can only observe the data cache, then the only change to the state is changing the mapping for the register x3 to the symbol s3 plus 8, nothing changing the observation. And then finally, when we execute the final load, right, we change basically the mapping again to the symbol x9. But what is important here is that we extend the observation list with an additional observation that is the actual value of the register x3, that is the original symbol s3 plus 8. So in one case, right, the symbolic execution will say that here there are only two options. In one option, in one case, if S1 is different than S2, that these are the initial value of the register X1 and the initial value of the register X2, then we will get this list of observation. In the other case, we will get this other list of observation, right? So this allows us to statically compute all possible lists of observations for the attacker. Well, now that we have this, we can basically synthesize the observational equivalence relation, the relation that guarantees that two states should be are indistinguishable for the attacker. And this is done by doing the Cartesian product between the final symbolic state that we obtain from the symbolic execution, right? So remember that for the first state, let's say the state A, the state 8 can only end up in two final results, right? So if S1 is equal to S2, it will observe S2 and S4, these two symbols. And if the register X1 was different than the register X2, then we will observe S2 and S3 plus 8. And the same thing happened for the state B, right? So if the state B, well, for the other state, can only have these two states. So we do the Cartesian product. And the final relation, what guaranteed basically that these two states, the two states are basically observational equivalent, is obtained by the conjunction of four different conditions. And the condition is basically done by making the conjunction of the two path condition and imposing equivalence of the observation. So for example, decide to follow this path, and the state B decide to follow this path, it means that A dot X1 is equal to A dot X2, and that B dot X1 is different than B dot X2, then it must hold that these symbols, this observation list, so A dot X2 and A dot X4, must be equal to B dot X2 and B dot X3 plus 8. So this is basically the condition that must be satisfied. So this allows us basically to build a relation that guarantee equivalence between the observation of two states. And then we use an SMT solver. Actually, we use Z3 and we ask, can you find a satisfiable assignment for these two states that guarantees satisfy basically this relation? And the Z3 solver give us an assignment to all relevant variables for the two states, right? So we say, well, I found out basically two states. For example, if you set x1 equal to 0 and x2 equal to 0 for the first state, and you set x1 equal to 5 and x2 equal to 0 for the second state, then also if you set x4 equal to 8 and x3 equal to 0, then these two states basically would be equivalent. Okay, so this gives us basically two states that we can use for the test. In practice, we need to add some additional constraint during this process because, of course, we cannot generate complete random states. For example, we would like to avoid the buffer overflow. We will only a region of memory is available for test because we have a limited amount of memory on the actual physical machine. So during this process, actually, we usually add some additional condition during this translation that inline some assertion that guarantee that the states that we get at the end satisfy this well-formed as property. That means all memory access are, for example, within a specific region, they do not have self-modifying code, and so on and so forth. Okay, so now we have two states that we can generate two random states that are observational equivalent, starting from a random program. How do we generate a random program? Well, we have not done much of research here, but we basically use a sort of monadic generator that is a sort of grammar that allows us to compose different templates. For example, we have a template that say you can execute a number of memory loads, you can execute a conditional jump, you can execute a sequentially compose a different program, you can, and then basically these generators are randomly instantiated. So we basically generate a random program that satisfies a grammar. and then we just send this program basically to the test generation. So for the test on processor, we implemented this for many processors, but I think the most interesting one has been the implementation for Raspberry Pi 3. That is a quite a common platform for that use the ARMv8 processor. This execution is coordinated by server, so there is a server that basically generates this random test and then coordinate like a cluster of Raspberry Pi 3 that execute the test on the actual board. On the board, we have a really minimal bootloader that load the random generated program. It set up the environment where we need to set up page table. We need to set up basically that the regional memory is cacheable so that we can measure the side channel. It set up the state A, that means the first state that we get from this process. So this has to load basically the registers with what is expected by this state. It executes the program from the state A. Then we expect the content of the cache so that we can simulate, we can measure basically the side channel. And then we clean the state, and when we repeat basically this process for the second state. And this is implemented in Trust Zone. This is a special execution environment in ARM that allows us to execute this in bare to metal. There is no noise. There is no operating system running below our test. This allows us basically to reduce the noise since we want to be conservative, right? We want to ensure that there is actually no way for the attacker to measure difference on this channel. And this also allows us to use some special instruction to read, to inspect the content of cache. So the result is that even like with random program generation, we have found some weird behavior. So in the case that we want to validate an access-driven attack that can probe the cache, the data cache, in this case, the observational model basically say, well, in this case, the attacker should only be able to observe the tag and index of these memory access. The attacker should not be able to observe basically which branch you have taken, and the attacker should not be able to observe the specific offset within the cache line that each memory access performs. So we have found many counterexamples to this. And actually, this counterexample seems to be related to an undocumented feature of the processor that we call pre-eviction. We contact ARM, and ARM has confirmed actually the existence of this behavior. Under certain conditions, the processor decides to evict some cache block early, and actually this prediction can depend on the cache line offset. So even if you follow twice this branch and you read here from the address 0 and here from the address, I don't know, 100, and you run again the same program, but instead of reading from the address 0, you read from the address 16, that is within the same cache line of the processor, so usually is considered undistinguishable for an attacker. We find out that the processor has a different behavior that can be actually measured by the attacker. So this can actually be used to build the side channel and extract information from secret information from a state. So we execute around 200,000 tests, and around 2% of the tests basically gave us interesting results. So gave us basically counterexample. And we run around 15 days. Of course, I mean, this is an automatic test. There is no one actually running the test physically. I mean, these are basically scheduled in batch, and then we have this server that coordinates the execution among multiple boards. I think we use 4 boards, so the actual test took basically 4 days. So, okay, let's go back to Spectre, because Spectre was actually the reason why we started this work. And Raspberry Pi 3, the board that we use for this experiment, is actually claimed to be immune to Spectre. So we would like to validate this claim. And the reason why this is claimed to be immune is because the processor has a speculative fetching. So the processor can speculative fetch instruction, but officially the pipeline is too short to be able basically to execute the instruction in speculation. So at least this was the original claim of ARM. So To validate this claim, right, we need a program template that generates something that has some condition. That's relatively simple, right? To generate a template that performs some condition, and in some case performs some memory load. Some other case does not perform any memory load. We need, of course, to modify our execution environment so that we can uh, train the branch predictor to basically take the wrong branch. So when the program should take this branch, we want to mistrain the branch predictor to go to the other branch. That's also relatively simple. One problem that we have is that it's really hard to find interesting example, interesting states. And I can show the reason on this simple example. So here we have a program that compare two registers, X1 and X2. If they're different, it does nothing. Otherwise, it reads from the address X3. And now suppose here that we say that the attacker can observe basically the address that we read, the address X3. So if you run the whole pipeline that I described before, we do symbolic execution, we compute observation equivalence, we get basically this relation, right? This relation say that, well, if A takes the left branch and B takes the right branch, then it's impossible for these states to be observational equivalent. So we will never find a counter example for this because they are already considered different from the model. And this same happened basically in the other case, right? So if the first state goes in this branch and the second state goes in this other branch, here we have a memory load, here we don't have any memory load. So these two states basically are always different. So there is no reason for test them. Okay? So in the other case, right, we have all the state where both states chose the right branch, and both states will have to access the address, the same address here. So both states need to have the same value for the register X3. But we basically know that all these cases will not be interesting, right? So in the case of misprediction, in the case the branch predictor decides to take the wrong branch before, in the other branch there is no memory load. So there will be nothing basically interesting here. The real interesting case for our study are the case where both states choose the left branch, choose to not perform the memory load, so they should be indistinguishable for the attacker independently of the value of the register X3. But if we look in the relation here, there is nothing here that constrains the register X3. So there is really low probability that the SMT solver will give us some state that only differ for the register X3, right? So the SMT solver may choose arbitrary state that satisfy this condition. For example, may just variate the value of the register X1 or may just variate the value of the register X9, right? It's hard to drive the test towards something that is actually useful. So to explain this, I want to introduce, to explain this a little bit better, if we look at an observational model, like the one that I showed before, this observational model basically partition the state in observation equivalence classes. So these are basically set of states that should be indistinguishable for the attacker. The observational model that I showed you before, it basically partitioned the state in these classes where we have a really large class, that is the class where X1 is different than X2, that is this one, that is actually the one that is interesting for us. And then some other class that say X1 is equal to the X2, and then since here we observe X3, we say, well, and X3 is equal to 0, then we have another class where X3 is equal to 1, and so on and so forth. So of course, these classes are quite large, right? Because they have inside many different states because the state space is really large, right? So we have all different values of the other registers, we have the content of the memory, and so on and so forth. So now starting from an observational model, we may of course define, let's say, weaker observational model that distinguish less. In this case, the observational class of this other observational model will be obtained by merging the observational class of our model under validation. So in this case, for example, if we only observe the result of the comparison and we don't actually observe the content of the register X3, all this class here will be merged in a bigger class that say we can only observe two large classes. The class where X1 is different than X2 and the class where X1 is actually equal to X2. And of course, we can define some more refined observational model where, for example, we can observe some more detail, right? So in this case, we will say we can observe the address that we access and, for example, the result of the memory node. This will sub-partition the equivalence class of our model under validation in some smaller classes, okay? So in theory, these observational models can build a lattice. We have a top observational model that is the observational model that where each class is a singleton, where you observe at every single extraction the full state. This observational model is necessarily sound because each observational equivalence class has only one single state. So assuming that the machine is deterministic, if we run twice the same program starting from exactly the same state, we should have exactly the same footprint on the side channel. Of course, this observational model is not really useful, but this will be sound by if we assume that the machine is deterministic. We, of course, have also a bottom observational model where we have one single class, one single equivalence class that say all states are indistinguishable. So between top and bottom, there is our model. And between our model and top, there are many other models, right? If our model is not correct, there must be another model in this chain that is more restrictive than our model, but less restricted than top, that actually introduce the observation that are needed to precisely model the side channel. So the intuition here is let's drive our test not only using the model under validation, but also using a supporting model that is a more restrictive model than the model that we want to validate, that somehow should represent some potential feature of the hardware that may affect the channel, and we want to rule out basically from the possible side channel. So in this case, we basically have two models to drive the test. We have model 1, that is the model under validation, and we have the model 2, that is the refined model. And we want to generate the test so that A is observational equivalent to B accordingly to the first model, but also A is not observational equivalent with respect B accordingly to the second model, so that we can generate tests that are actually useful. So if we go in the case of speculation, the refined model basically will add observation in its branch that correspond to what can happen in speculation. So if we go in this branch, right, that is basically the branch in a position in location 4, if we start from this original program, in the right branch, right, we don't have to inline any additional observation, because if the processor decides to take this other branch in speculation, in this case, nothing happened. So here we don't inline anything more. This branch 4 is basically exactly equivalent to the branch 4 that we had before. But in the location 8 that was empty before, we need to align the observation that can happen in the case that the processor decides to mispredict and take the other branch. So in this case, we can inline basically the observation X3, because in the case that the processor take the wrong branch, the attacker will be able to observe the value of the register X3. So now we have two types of observation, the observation 1, that are the one of the model under validation, and observation 2, that are these shadow of observation that are introduced to represent the refined observation. So now we run the whole chain again, but with the additional constraint that the state should be observational equivalent according to the first model, and observational not equivalent accordingly to the second model. These two pairs of states is still impossible, but if we look at again to this class, to this pair, so in this case, we'll say, well, there is no reason to test this branch, because if x1 is equal to x2, and x1 is equal to x2 also for the second state, so if both states decide to take this branch, there is no way to get an interesting result, because it's impossible to show that these states will be distinguishable accordingly to the second model, accordingly to the speculative model. So we can completely rule out all experiments that go in this class. While for the experiment that decide this other branch, so where when both states decide to go on the left branch, right? This system say, well, if you want to guarantee distinguishability accordingly to the refined model, that is the model that takes speculation into account, you need also to guarantee that the value of the register x3 for the first state must be different than the value of the register x3 for the second state. Okay? Well, do we get this? Well, of course, we also needed to extend the pipeline with the branch with the mechanism to train the branch predictor, so that we ensure that when we execute these two states, we can train the machine to go to the wrong branch, because now we want to take states that should go in this branch and train the machine to take this other branch in speculation. This is done by just extending the pipeline and use the SMT solver to generate basically to generate a state that satisfies the other conditions. So if in the relation we say that a dot x1 is different than a dot x2 and b dot x1 is different than b dot x2, then we just ask with SMT solver, well, take the other path, so generate a state that satisfies the other path, and then we use this state C to train the branch predictor. So we execute the machine multiple times with this state, so that we train the branch predictor to take the wrong branch, and then finally we execute the test with the two actual, we execute the program with the two actual test input. And what we get is that, well, it's not true that Raspberry Pi 3 is immune to speculative execution. We actually found a new speculative that can leak data when you have one single speculative load inside the branch. So if you have exactly this program can actually execute this load in speculation, even if ARM initially claimed that Raspberry Pi 3 is not able to perform this speculative load. So if we execute this program, this can leak the value of x3 when these two, even if these two registers basically are different. We execute around 16,000 tests and on around 600 random programs. And without refinement, we were able only to find two single condor examples to our observational model. Using this refinement approach, we were able to find around 25% of the experiment were counterexamples. And these counterexamples that we were able to find here were counterexamples for some really specialized program, like in the case that the comparison here between the two registers were using the same register that we're using here in the load. So this basically allow the SMT solver to generate something useful, because the load here that was using in speculation was basically the same register that was also used here in comparison. But the majority of the program basically we were not able to find counterexample. While using this refinement approach that allow us to put an hypothesis, basically to use a second observational model to somehow phrase what are the potential microarchitectural features that may affect the side channel, drastically increase the number of counterexamples that we can find on the platform. So some concluding remarks. So the existing observational model are often overlook some information flow. This has been already demonstrated by Spectre, and we show that we have found many low-level feature of, for example, Raspberry Pi that broke existing observational model. And without some observational model, we cannot really reason about software security, because we cannot really reason about absence of side channel on programs. And seems that this observational equivalence and model refinement provide a good strategy to drive the test, right? So we were able to find many undocumented features in off-the-shelf platform, and these are widely available platforms used. I don't know how many millions of Raspberry Pi 3 they have sold around the world. So some new challenges that we are currently investigating. So once we find that the model is wrong, we have a counterexample, and will be nice to have a mechanism to repair the model, right? So if we go back to this lattice, if this model is wrong, we have found a counterexample. It would be nice to somehow push this model up in this lattice to try to repair the model automatically. This is something that we have not investigated, but this is something too interesting to investigate. For now, we only analyze side channel for user level instruction set architecture. Would be interesting to see what happens when you use some privilege instruction, or side channel that can happen when the program interacts with some physical device like a network interface controller